All right, we've actually got more quantum numbers than just N and L. We've also got quantum numbers that predict how many orbitals each of our subshells will have, and then the spin on the electron that is in a particular orbital. So the first one is the number of orbitals. This gets the designation of M sub L, so like the L is a subscript. And these values are allowed to be anywhere from negative L up to 0, up to positive L. And they have to be, of course, integers. So for example, when your L is equal to 0, we have an S subshell. In this case, M sub L can only equal 0. And since we only have one value of this, we only have one orbital, right? So that just looks like the circle. And so there's one S orbital per N, right? So N is equal to 1, we'll have one S orbital. N is equal to 2, we'll have one S orbital. N is equal to 3, we'll have one S orbital. They each get one S orbital per N. Then when your L is equal to 1, we have the p orbitals. Our M sub L can now be -1, it could be 0, or it could be +1. You can see in this case, we have 1, 2, 3 values of M sub L. And so those correspond to our 3 orientations of our p orbitals. And so we have 3 p orbitals per N, right? In this case, it starts with N is equal to 2. So your N is equal to 2, you'll have 3 orbitals. Your N is equal to 3, we'll have 3 orbitals, right? 3 orbitals each. And then finally, the last one we're going to go over, L is equal to 2. We call those d orbitals. Then M sub L can be -2, -1, 0, 1, or 2. And again, we have 5 values here. So that's where the 5 orbitals come from, right? So they look like these 3-leaf clovers. So that covers 4 of them, right? So you have one like that, and then 3 more in different orientations. And then you have the dumbbell with the ring, right? So in this case, there are 5 d orbitals per N. And again, the reason behind all of this is very complex mathematics that we're not going to go into. And so these electrons reside in specific orbitals. So we can think of these orbitals as the homes of our electrons. And in this case, we get 2 per orbital, so 2 electrons for every 1 orbital. And these electrons individually get a spin value. We call this M sub S, so lowercase m with a subscript of S. And these can either be +1/2 or -1/2. And so that represents spin up or spin down. So for example, in the 2s orbital, we could fit 2 electrons there, 1 spin up, 1 spin down, and that represents this spherical orbital. In the 2p orbitals, we're going to have 3 of them, and we could have up to 6 electrons. 2 per each of these individual orbitals, right? And each one of these orbitals represents one of our orientations of our dumbbell-shaped orbitals. And so the rule in quantum mechanics is that no 2 electrons in the same atom can have the same 4 quantum numbers. This is what's known as the Pauli exclusion principle. Another thing you can think about with these quantum numbers are N, L, M sub L, and M sub S is our addresses for our electrons. They'll tell us where we can locate the electron, right? And so obviously, people living in different houses can't have the same address. And even people living in the same house, yes, they have the same address, but if a piece of mail is coming to you, it's going to have your name on it, right? So we can think about these quantum numbers as the address for our electrons.